Good morning or afternoon, everyone. We are from Group CSC645 and today me and my team will present our project titled E-commerce stock finder system using a binary search tree. This project focuses on using the binary search tree or BST to improve the efficiency of searching product information in an e-commerce inventory system. This presentation consists of six main sections. First, we will introduce the project including the background, problem statement, objective, and the scope. Then we will explain our team roles followed by the real-life scenario, the proposed solution using a binary search tree, the implementation analysis, and finally our conclusion and future improvements. Next is our project backgrounds. As we know, the rapid growth of e-commerce platforms such as Shopee, Lazada, and Amazon has increased the needs of efficiency, inventory management. Each product is identified using a unique SKU. In our project, we use a binary search tree to organize the products, allowing faster searching, insertion, and deletion compared to a normal list. On average, BST can achieve zero log and search time, making it stable for large inventories. Next is our problem statement. There are four main problems. First, e-commerce warehouses manage a very large number of products. Second, using linear search becomes slow as the number of products increases because it has zero and time complexity. Third, during major sales such as 11.11 and 12.12, the number of sales requests increases significantly. Finally, slow product retrieval can delay the processing and reduce the customer satisfactions. Next is our objective. The objectives are as follows. First, to design and develop an e-commerce stock finder system using the binary search tree data structure. Second, to implement ST operations for inserting and searching product record based on SKU numbers. Third, to analyze BST searching performance against the linear search algorithm through time complexity analysis. And finally, to demonstrate the effectiveness of BST in improving stock retrieval efficiency within an e-commerce system. Next is the project scope. Our project scope includes storing product information such as SKU, product name, quantity, and the stock status. The system can insert new product into the BST as product using the SKU, display product information, and compare BST with linear search. However, features such as customer accounts, online payment, shipping management, database integrations, and product recommendations are outside of the scope of these projects. Now let me introduce our team members and their responsibility. Our Najib Farhan is our project leader and system designer. He manages the project planning, coordinated the team, and designed the overall system architecture. Me, myself, Kabrian Anak Sabang, as the system and algorithm developer, I designed and implemented the various tree, developed the insertion and searching algorithm, and carried out the complexity analysis. And our next member is Muhammad Zaim bin Muhammad Atan. He is documentation and testings, and he prepared project documentations and presentation, tested the system, and compiled the final report. Next slide, I will pass to my team member.
My name is Muhammad Zaim and I will be presenting the real life problems that we can look at. Let's look at real example in Malaysia. In early 2024, Shopee and Lazada in Malaysia made about USD 530 million together during the Ramadan sales. That's a huge number of customers checking stock at the same time. The problem comes when many small sellers still keep their stock list as a simple spreadsheets, check one item at a time. Before a big sale, sellers need to check if items are in stock, get warned when best sellers are running low, and check stock for each product variant too. Every one of these checks mean searching through the whole list. So if this flood of stock checks is what causes the problem, then we will look at the next slide. The actual problem comes when the stock is stored in a simple list. The system has to check items one by one. This is called linear search. The more products you have, the longer it takes, and stock key list keeps changing. Sellers add new items all the time, especially right before a sale. So we need something that's fast as both adding new items and finding them. That's what a binary search tree does. It keeps them in order, so both jobs stay fast. Why does this matter? Well, if searching is slow, it doesn't just look bad, it causes real problems. If the system takes too long to check stock, a shop might accidentally sell something it doesn't have. On the other hand, if sellers can trust the system to check stock fast, they end up keeping extra stock just in case, which wastes money. Studies also show that slow searches lead to slower deliveries, and during big sales, even a tiny delay adds up fast when thousands of people are searching at once. This can slow down the website, break the checkout, and lose sales.
Okay, so for the next one is the proper solutions, where this system will use the binary search tree algorithm, where BST is in hierarchical non-linear structure. And for the right hand side, we can see the example of the illustration on how the system will be designed using binary search tree. And for the next one is the system architecture, on where it shows the structured pathway from a user instruction down to algorithmic data processing, where for the first layer is the customer, which is they enter the target ID, and for the front end, it will search and the query for the engines. For the next layer, it will compress the target ID with the current node, and next, it traverse the left and right branch down to the tree. And for the last layer is it return the product data, which is it shows the name, stock count, and price data. And algorithmic operations. It have two main code that it will insert in the BST coding. The first one is stock insertion, where it handles the root and recursively compare ID against existing nodes. And next is the stock searchings, where it compare the pointer node and the system shift left or right until it finds the match or empty branch. And for the next one is the output, where the product shows the 20 and the result, and it shows the result, which is the RGB mousepad. And for the left hand side result is for the product ID is 30, where it successfully shows the wireless mouse within 88,800 nanoseconds. And for this section, it will compare the linear search and the binary search difference. In terms of average looking speed, linear search is slow, while the binary search is fast. In terms of insertion performance, the linear search is fast, while BST is balanced. And for the structural scalability, it pour under the high data load, while binary search is high under high load data. And in terms of data ordering, linear search will be the unordered sorting, while in binary search, we will automatically self-maintain the data. And for the performance and discussion limitations, and for the system performance, it decreasing search step from the linear scale curve to logarithmic progression lets the system sustain fast response even during the peak high volumes. And for the limitation, this system depends heavily on the insertion order, where its record insert in sequential order that can wrap the tree into the single site in efficient layout. And for the recommend, it will adopt a soft balance variant such as AVL3.
To sum up, we built a stock finder system using a binary search tree with each product's ID as the key. It can do two things: add new products and search for them. Each time it searches, it cuts the remaining choices in half, which is why it's fast. This connects back to our earlier example, Shopee and Lazada making 530 million US dollar during peak sales shows just how many searches a system like this needs to handle. On average, our tree can find an item in all log n time, while a simple list takes all n time much slower. There is one weak point. If items are added in perfect sorted order, the tree can turn into something just as slow as lists. But overall, this project shows that choosing the right way to store that data really does make a system faster and more reliable, which was our main goal from the start. Some of the future enhancements that we can do is, firstly, we use a self-balancing trees like an AVL tree, which will keep the tree fast no matter what other items are added in, fixing the weak point we just talked about. And then the second one is to add proper storage. Right now everything is stored in a memory, so a real system would need to save data to disk using something like a B plus tree. And the third one is to allow searching by more than just ID. Sellers should be able to search by category, price, or how much stock is left. Fourth, make it handle many people at once safely, so two sellers updating stock at the same time don't cause errors. And finally, connect it to live stock data from different sales channels so stock numbers stay accurate everywhere and shops don't accidentally oversell.